Here are solutions to homework set number 3 for ECE 376. The first problem is given an RGB LED like the one in your lab kit. Come up with the hardware to connect them to your PIC board so I output 20 milliamps to each LED. Well, LEDs are diodes. The voltage drop across the diode ideally is constant. So at 20 milliamps, this is 2 volts. At any current, it's roughly 2 volts. That's an ideal diode model. The remaining voltage is across the resistor. Assuming the PIC outputs 5 volts, then the current is 5 minus 2 over RR. Or going the other way around, the resistance should be the voltage drop across the resistor divided by the current. The red resistor should be 150 ohms for 20 milliamps. The green and blue should be 90 ohms for 20 milliamps. So if I do that, I'll have the PIC driving the red, green, and blue diodes at 20 milliamps. Then in software, when I output logic 1 to each pin, I'll turn on or off the various LEDs. Problem 2 is design a circuit that lets you turn on and off a 5-watt white LED. Now the difference between problem 2 and problem 1 is if your load is less than 5 volts, less than 25 milliamps, you can drive it directly with a PIC. If you need more than that, I need a transistor. So if I have this LED, assuming it's 6.5 volts, again the specs say between 6 and 7 volts, I chose 6.5, and 100 milliamps, a PIC can't do that directly. But what I can do is use a transistor as a switch. When the PIC is outputting 0 volts, here's the diode. If I have 0 volts across the diode turns off. If there's no current in the base, there's no current in the collector, there's no current flow, the LED is off. So turning off the LED is really easy, just output 0 volts. The hard part is when the PIC outputs 5 volts. I want the LED to turn on. By on, I mean 100 milliamps. To set the current flow, I use RC. Assuming a 12 volt power supply, I've got 6.5 volts across the LED. The transistor, when it's turned on, is about 2.2 volts. That's what we assume for a saturated transistor. Leaving the remaining 5.3 volts across that resistor. 5.3 volts at 100 milliamps is 53 ohms. So that sets the current. To turn on the LED, I need to use the base resistor. The basic equation you have is when you saturate, I want beta IB to be more than IC, which is 100 milliamps. If I divide by beta, that's how much base current I need. So I need at least 0.33 milliamps. It's pick RB anything you want, so this is bigger than 0.33 milliamps, less than 25. The 25 is all the PIC can output, so pick any number between 0.33 and 25. I chose 4.3. Once you pick the resistance, or pick the current, then the resistance is the voltage drop across that resistor. So here's 5 volts, 0.7 volts, 4.3 volts at 4.3 milliamps, makes that 1K. And there's actually a lot of room for slop. It's anything between 0.33 and 25 milliamps works for RB. Problem 3 looks at timing. Suppose I want to drive a speaker, and it's kind of the same circuit. If I want to drive a speaker at really loud volume, I can replace this with 8 ohms. And this will turn on and off the speaker. Well, too much current, but make that a speaker versus LED, I can get different amounts of current. If I want to play the note F3, I want to output a square wave. And the frequency of the square wave tells you the frequency of the speaker. So this is 174 hertz. The time between toggles should be 10 million divided by 2 times hertz. That's the number of clocks. So this distance right there is 28,000 clocks. 28,635. And likewise on the low side, that's also 28,000 clocks. Now I need to come up with a wait routine that burns 28,635. Here is one wait routine. So this inner loop burns 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 instructions means 9 clocks, plus 1 for go-to. This is 10 clocks. That is executed 239 times. That is executed another 12 times. So the total time for that wait loop is 10 times A times B, plus this part of the code, 1, 2, 3, 4, plus 1 for go-to. 5 clocks is executed A times, plus 1, 2, 3, 4. So that wait routine is 10 times A times B, plus 5 times A, plus 4, plus main routine calls it, runs a couple clocks. That doesn't really make a huge difference. I want to find A, B, and C so that the total is 28,635. Subject to the constraint that A, B, and C or A and B are integers, and the numbers have to be in the range of 1 to 255. These are 8-bit counters. The biggest number I can store in 8 bits is 255. So play around with A, B, and C to get close. One combination is 239 for B, 12 for A, and the way I founded that is I start with 255 for B, find A, round up. Once I find A, then find B. And they get you close, 28,749, off by just a hair. And I can check that. If I say run that code, so I'm taking the output, going through a 200 ohm resistor to a speaker to ground, makes a nice pleasant noise. Measure that frequency with the piano tuner app on your cell phone. It's like 173 Hertz. Or my multimeter also has a frequency scaling, so put that on frequency, measure the square wave at RC0 and the output. It's actually more accurate, 174.1 Hertz. I designed the code to be 174.61 Hertz. It's actually 174.1. The reason it's a little bit low is because when I found the wait loop, it's a little bit too long. Plus there's extra lines of code that I ignored. Like this part of the code, I'm not really counting. But that takes, 1, 2, 3 for go-to for 5 clocks. I'm up by maybe 5 out of 28,000. Net result is it's pretty close. That's the beauty of assembly. I can count instructions and tell you exactly how long it takes to execute. If you want to kill yourself, you can sit there and fine-tune the code and get it dead on. But for now, that's good enough. Problem 4. Write the code for an LED flashlight. And what I want this to do is the following. When I hit RB0, the flashlight turns off. Hit RB1, the lights blink on and off every 100 milliseconds. RB2 turns on for a second, off for a second. RB3 is full on. You can change it. So that's what I want to do. How do I do that? Well, the first step is write the flowchart. So here's one possible flowchart. I'm going to initialize port B to input. Those are my push buttons. Initialize port C and D are output. That's where the lights are. Then go into a loop. I'll first have this variable called mode. I'll read the buttons and tell you which mode you're in. And the way the code's written, this is for debugging purposes. I am displaying the mode right here on port A. That's kind of nice for debugging, so you can tell what's happening. So here I'm in mode 0. There it goes. Mode 0, lights are off. Mode 1. Mode 2. And mode 3. And then I check the mode. If I'm in mode 0, I turn off the lights. Mode 1, I'll toggle every 100 milliseconds. Mode 2, toggle and wait 1 second. Mode 3, turn the lights on, then repeat. That's the flowchart. The code, each section of the flowchart corresponds to a section of assembly. The initialization is right here. I'm going to write FF to tris B, clear tris C and tris D. That sets the I/O pins. Port B is input, C and D are output, and everybody binary. This first label, I'm going to have too many labels in here, but that kind of sees what's going on with the code. I'm going to check the button. If I hit button 0, I'll go to label 2. Hit button 1, I go to label 3. Hit button 2, I go to label 4. Button 3, go to label 5. Otherwise, go to label 6. At label 2, I make the mode 0. Label 1, mode is 1. Label 2, mode is 2. Move 2 to W, move W to mode, and so on. Last part. Check the mode. If I'm in mode 0, go to label 7. Mode 1, go to label 8. So let's move 1 to W, compare skip if greater than, go to 8. I actually want to do on 1, I go to 8. So if it's equal, I don't skip. And since I'm starting from 0, it's never less than. So that goes to the different spots in the code. To implement it, this is clear. I want to turn off the lights. I clear port C and D. Go to label 1. To toggle every 100 milliseconds, I'm going to toggle the pins, call the wait loop 100 millisecond wait, then return. And we'll get to this in just a sec. For a 1 second wait, same thing. Wait 1 second, then return. And to set, I just set. Now the wait routine I'm going to have, this is waiting 10 milliseconds times W. 10 milliseconds is 10,000 clocks. So here is 9 clocks, executed 100 times, executed 100 times. Actually, that's 9 plus 1 for go to makes 10. That gives you 10,000 clocks, which is 10 milliseconds. And that is executed whatever's in W when I call this. So that's 10 milliseconds times 10 gives you 100 milliseconds. 10 milliseconds times 100 gives you 1 second. And the net result, right here, here's off. 100 milliseconds on, 100 milliseconds off, so it's 5 flashes per second. 1 second on, 1 second off, and full on. For problem 6, that's tester code. That's kind of what I was doing here, checking the different buttons, making sure I am in the right mode, then checking the lights to see if they're on or off. If you have an oscilloscope, I can check the timing. Otherwise, you kind of ballpark it. And the last part is demo, either in person or video or demonstrate on Zoom, any of those. So it's homework set number 3 for ECE 376.